Hello everyone. In this video we will continue examining topic 4.4 wave behavior, and in particular we will begin to look at two-dimensional interference and the double slit interference pattern. All right, so interference is a topic we examined earlier in waves. Recall that in one dimension, constructive interference occurs when the displacement of two waves at the same point is in the same direction. So remember that interference in general is a name for the phenomenon when the two waves are in the same place at the same time. And constructive interference is when those two waves have displacements that line up or add up. Remember that interference is a weird name for this, in part because they're not really interfering with each other. They're in the same place at the same time and giving sort of this result that they add up, but then they continue onwards. This is a sort of a strangely named phenomenon. But not only can you have constructive interference, you can have destructive interference. And this occurs when the waves that are in the same place at the same time have displacements in opposite directions. So this particular wave pulse has a positive displacement, this one has a negative displacement, and so when they are in the same place at the same time, they cancel out. A good rule of thumb is that constructive interference you think of as sort of adding up, and then destructive interference you think of as sort of canceling out. And the general phenomenon by which you determine whether they are adding up or canceling out is known as the principle of superposition. So you superimpose the two waves on one another and see how they interact that way. So the general idea then is that two-dimensional and three-dimensional waves also demonstrate interference, both constructive and destructive, and we'll return to that in a little bit. But our first idea, or the first most important application of this idea of interference, will be known as the double slit interference pattern, or double slit effect sometimes, or the double slit experiment. Quick word of warning, this is one of the most complex topics and most challenging topics in the standard level syllabus, and so you may need to go over it a couple of times. There'll be a number of videos attempting to get at the same idea, and this is just the introduction. So, to dive into this, Thomas Young in 1801 demonstrated what appeared to be sort of conclusive evidence that light was a wave, and he did so by demonstrating that light undergoes interference patterns, and we'll explain what that is in a second. So this is the double slit experiment, originally conducted by Thomas Young in 1801. And the general idea is that if you take laser light and you shine it on two narrow, closely spaced slits, then that light goes through both of them, and you get sort of a surprising result. Normally, if you shone light on two slits, you might expect sort of on the background to see sort of two bright beams of light. Imagine you had a window, and in that window you shine a flashlight, and you had sort of two slits the way you might see in, an old-fashioned castle or something. You'd expect to see sort of an outline of the window on the back wall, right? Those maybe two bright lines. As it turns out, in this experiment, you do not see that. You see something certainly more interesting and more complex. And what you see is, in fact, bright lines or bright fringes, more than just two of them. You see quite a few of them, depending on your setup. And in particular, this image right here captures what those fringes look like. You see bright spots closely spaced to one another on the back wall in this characteristic double slit fringe pattern. All right, and we're going to seek to explain this, but the fundamental idea is that you need to ascribe to light the properties of waves in order to explain it. This is an evidence or a significant piece of evidence that light behaves like a wave, and was one of the first pieces of evidence that was very, very convincing in this respect. So let's talk a little bit about why this happens, and what about waves allows us to make this prediction that this would happen. So when that coherent laser beam, so that laser beam full of light, all with the same wavelength and sort of at the same point in their wave, this is part of what makes a laser, hits those two slits. Remember, those slits are very small and close together, so that light is covering the whole area where those slits are. Then what happens is that the light basically comes from both slits independently. It's as if you had sort of two tiny lasers right next to each other. And each of them produce outgoing wave fronts that spread out. And fundamentally, here's the general idea. Those wave fronts, as they spread out and hit the back wall, are sometimes lined up, sometimes perfectly lined up, to give you a bright spot on the wall. And sometimes they're not lined up, and you get destructive interference. Where they lined up, you got constructive interference, and where they didn't line up, you got destructive interference, and that gives you fundamentally this fringe pattern. So, if that's a little bit confusing, we're going to go through a number of ways of examining that concept qualitatively, and then we'll tackle it quantitatively. So, first of all, recall that for a continuous wave, interference looks something like this. So if two waves, take a look at the top purple wave and that bottom blue wave, start at the same point at the same time, and they have the same wavelength, so they're in phase, then they will add up and you will get constructive interference. If one of those waves, however, is slightly offset, perhaps by exactly half a wavelength, then, as you can see in these two waves here, if the purple wave is at a peak, then the blue wave is at a trough, and so if they superimpose and are in the same place at the same time, they're half a wavelength out of phase, and you get perfect destructive interference. But again, if the second wave is emitted just a little bit after that, okay, in fact, another half wavelength, then even though they're not at exactly the same place, this blue wave may have started before this purple wave, you can see that in their wave structure, they're in phase again. So they are at the same place at the same time. The peaks line up with the peaks and the troughs line up with the troughs, and so you get perfect constructive interference. So keeping that in mind, here's the fundamental idea. Light comes to the wall from both slits, and imagine for a second that it came and light is going to sort of end up from both of those slits on that back wall. The spot right in the center, well, that's the same distance from both slits. And because it's the same distance, you'll have exactly the same wave shape appearing and arriving at the wall in phase. It's the same distance from the top slit as it is from the bottom slit. As a result, you get a very bright central maximum, known as the central maximum. And that bright spot is right in the middle of the pattern. It's right that center bright spot, and you're getting perfectly constructive interference. But then, if you go a little bit above that, okay, and this picture exaggerates the effect, just so that we can see it. But if you go a little bit above that, you can see that the light from the lower slit has farther to go to get to the wall than the light from the upper slit. I'm going to repeat that because that is the essence of what is going on here. The light from the lower slit has farther to travel than the light from the upper slit. And as a result, the light from the lower slit is at a different point in its own wave pattern than the light from the upper slit. And in fact, you're going to get a perfectly dark spot and perfect destructive interference if the extra distance the light from the lower slit has to go is exactly half a wavelength, just like that. And if it's exactly half a wavelength, remember you get the two waves cancel out and you get destructive interference. So the extra distance that this wave, this lower wave, has to travel is exactly half a wavelength. But if you go above that point on the wall here, sort of zoomed in a little bit in this diagram, so you keep moving upwards on the wall, now the light from the lower slit not only has to go an extra half wavelength, in fact, it has to go an extra full wavelength. And so those two waves, the one from the lower slit and the one from the upper slit, line up again, and you get perfect constructive interference again, giving you another very bright fringe on the wall. And so the general pattern that we've just discussed would give you a bright fringe right at the center, where there is no difference in the path length, a dark spot, okay, where there is exactly half a wavelength difference, and then a bright spot, where there's a full wavelength difference. This is fundamentally responsible, this pattern, so bright, dark, bright, continues onwards and is fundamentally responsible for these fringes here. For each of those bright spots, you have a path difference of a full wavelength, or, as it turns out, an integer number of wavelengths. But we'll talk about that more in the next video.